This is the solution to the Spring 16 exam, problem 54. This is a Newton's cradle style problem where you have a larger mass, this time 2m, and a smaller mass of m. They're both hanging from a wire, and the mass of 2m is swinging and collides with the mass of small m, causing it to swing upwards to a height h above its initial height. We are asked to derive the velocity of this mass, which we'll call mass 1 and mass 2, in terms of the height of mass 2. So this is an elastic collision, and that means that in addition to conservation of momentum, we also have conservation of energy. And you'll recall from the unit on elastic collisions that conservation of energy can be used to derive an easier non-quadratic relationship, which is that the relative velocities of these two masses is the same after the collision as before, but with a minus sign. So before the collision, if you were sitting on this mass, you would see this mass coming towards you with some relative velocity. After the collision, if you were sitting on this mass, you would see this mass going away from you with the same velocity, but in the opposite direction. We can write that out as v1i minus v2i equals negative of v1f minus v2f. And since v2i, this is initially stationary, we can put in a 0 there. So that's our conservation of energy derived relationship, but with an elastic collision, we also have, and with an inelastic collision, in all cases we have conservation of momentum, which tells us that the initial momentum of the system, and this is the only moving mass, so we have 2m v1i, is going to be equal to the final momentum, which is 2m v1f, so the final velocity of this times its mass, plus mv2f, which is the final velocity of this times its mass. And if we substitute this relationship, which we got from equation 1, that v1i plus v1f equals v2f. So we're going to substitute this into here. We get that 2mv1i equals 2mv1f plus m times v1i plus v1f. And now we have that 2mv1i equals 3mv1f, that's just combining the v1f terms plus this mv1i. We bring it over to that side, and we get that v1f is equal to v1i over 3. So the velocity of this is, the final velocity of this mass is going to be 1/3 of its initial velocity, but it's going to be continuing to go this way. Now, in order for the relative velocity of this to be the same but flipped, this actually has to be going faster than the initial velocity of this. And when we substitute in v1i over 3 into this equation here, we get that v2f is equal to 4/3 v1i, which is consistent with what we're saying, because then this relationship holds true, that if you were on this, you're now seeing this going away from you at the same speed that it was coming towards you initially. So now we need to define this v2f. We need to relate it to the final height that it will come to. So immediately after the collision, this is going to have this velocity v2f. And so it's going to have this kinetic energy of 1/2 mv2f squared. But when it gets to its highest height, it's going to be equal to its total potential energy, which is mgh, which means that v2f has to equal square root of 2gh. We know that v1i is 3/4 of v2f from this relationship here. And so therefore, v1i equals 3/4 the square root of 2gh. We bring that into the square root, we get 9/16 times 2gh, which gives us 9/8 gh inside that square root, and that gives us our answer, which is B.